This set of notes discusses software design using inheritance. Now that we have studied this object-oriented feature a bit, let's step back and look at the big picture one more time. Note that inheritance and polymorphism are powerful object-oriented tools, but they are not always necessary in our programming solutions. After all, we are more than halfway through the semester, and although we have been implicitly using Java's built-in hierarchy structure, we haven't had to explicitly design any code that included hierarchies ourselves. Inheritance design issues. What do we need to consider when building class hierarchies? Let's look at a few of the inheritance golden rules. First, we should only use inheritance when our classes are in an is-a relationship. This means that as long as one class can be described in terms of the other class, such as German Shepherd is a type of dog, or orange is a fruit, or square is a rectangle, and rectangle is a shape, then it is wise to use inheritance and polymorphism. These relationships are all around us as we frequently classify things. It has also been my experience that it can be very useful for cleanly coding exceptions to the rule. One noticeable truthiness about programs is that we seem to write 75% of the code to manage things that may happen less than 5% of the time. An example of this might be if we had to program a bowling scorer. We would create a frame class. Now frames 1 through 9 are scored in exactly the same way, so we could easily create frame objects for each one. But frame number 10 is a frame, but scored differently sometimes. Here it would be a cleaner design to create a subclass of frame for the special 10th frame and let that subclass manage the differences, like a possible third role. This way we don't complicate the parent frame class. We need to find common characteristics of the classes and move them as high up in the hierarchy as possible. The beauty of inheritance lies in our ability to reuse code instead of rewriting code. We should make every effort to avoid redundant or repeated code. This is a similar concept to writing methods and passing a parameter. One set of reusable code is preferable to copies of repeated code for different variables or objects. Just as we want to write set player name once and reuse it for every player in a game, we want to code our superclass with as many common properties and behaviors as possible. Then we inherit them into the subclasses instead of copying and pasting code. As programs grow larger and more complex, it is much easier to manage and maintain software that does not have a lot of redundancy. I have learned this from experience. Unnecessary repeated code is a nightmare. If you find yourself copying and pasting code, stop. See if you can find a better coding solution. Overriding methods is where the polymorphism comes into play. When all of the subclasses need to perform an action that needs to be done differently depending on the object, then overriding a common abstract method is the right way to go. A few examples. In a payroll program, all of the employees need to be paid, but different job classifications require a different method for calculating pay. So we would make calculate pay an abstract overridden method in the superclass and then override it in each subclass of the unique job categories. Likewise, in the bowling game scorer program, we would override the parent frame class score frame method in our 10th frame class, since we need to score the 10th frame, but possibly do so differently from frames 1 through 9. More design issue do's and don'ts. Add new variables to subclasses as needed. but don't redefine inherited variables. This is called shadow variables, and it leads to hard-to-find logic errors. For example, we do not need to redefine a variable for net pay in every subclass of our payroll program. We just inherit that variable from the superclass. Likewise, we would not want to redefine role 1 and role 2 in the subclass of the 10th frame of our bowling scorer program. We would just want to define role 3, a special characteristic of the 10th frame. We need to code each class to manage its own data variable members. Put the setter and getter within the same class as the instance variable. This creates a cohesive class design. Remember to invoke the superconstructor to initialize the variables that were defined within it. You may need to pass information as input parameters to the superconstructor. If so, be sure to code it as the first line in the subclass constructor. Even if there are no current uses for them, override general methods such as toString and equals with appropriate definitions. We have been careful to do this with the toString method for our classes. After all, this is overridden from class object, and we frequently need to be able to display the contents of an object as a string. Another popular overridden method from superclass object is the equals method. Each class can define what it means for its object to be considered equivalent to another like class object. Equals will always have one input parameter that matches the class type. Perhaps, for a personal contact object, that would just be verifying that the input object has the same name as the current object, while other variables such as phone number and/or address could vary, because we are just interested in identifying a particular individual as the same or equal to the current object by name. Other design tools we can include. Abstract classes and methods. We already talked about the power of overriding abstract methods. We can also define abstract classes. Remember that an abstract method is a placeholder method. It has no definition. Why not? Because we are just using a placeholder for what has to happen, not how it gets implemented. Remember our calculate pay method idea. An abstract class is also a placeholder class. We will never actually create any objects of an abstract class. We're not allowed. We use it to manage the common members of the subclass. In our payroll program example, it is likely that every employee at the company will be an instance of a subclass for a job category. Then it is wise to make the superclass employee abstract, knowing that every employee will be instantiated from one of the job category subclasses. Note how this is different from our bowling scorer program. The superclass frame would not be a candidate for an abstract class, and score frame would not be labeled as an abstract method. Why not? Well, because we will be instantiating frames 1 through 9 from superclass frame, and we will be providing a code definition for score frame method that works appropriately for frames 1 through 9. The visibility modifiers, public, protected, and private, give us a lot of control over what parts of the code can access and/or modify or mutate the members of the class. We still need to think like paranoid programmers, but with good style. In class hierarchies, we may need the subclass to have direct access to a superclass variable, so we make it protected. This allows other classes within the family tree and project access to the member. But good style dictates that we limit using protected on an as-needed basis. Although a member may be private in the superclass, we still can inherit it. We just have to use the superclass set and get methods to use it. Remember our class mantra, paranoid programming, but also with style. Restricting inheritance with final. We have already seen the use of reserved word final with class instance variables, essentially making them constants. The use of final with a method means that a subclass is not allowed to override it. In other words, if it needs this method, it will have to use this one, not its own version. Similarly, if a class is defined as final, then it has been neutered. There can be no children derived from it, and so it will never have any subclasses. Note that an abstract class can never also be defined as final. The point of an abstract class is to define subclasses from it, and final would not permit that. These are key design decisions, establishing that a method or class should be used as is. Inheritance design conclusions. Wow, lots to consider when designing and programming with inheritance. Taking the time to create a good software design reaps long-term benefits. Inheritance issues are an important part of an object-oriented design. Properly designed inheritance relationships can contribute greatly to the elegance, maintainability, and reuse of the software. It takes practice and extra time planning your design. There is no precise formula or one right answer, but we do have these guidelines. Clearly, designing and coding software solutions is a creative process, and many solutions are possible, but not all are elegant or even acceptable. Now that we have added this new level of complexity, be open to practicing and continued learning and self-improvement. You will always need extra time for the design phase anytime you use class hierarchies and inheritance. Happy coding!